Right. Okay, we are finally ready. Thank you very much all for being here. And I don't want to lose any more time. The speaker of today is Valentina Pederzoli for Politecnico di Milano. And let me thank the CIM student chapter that will offer a refreshment at the end of the seminar. And I guess that we can start. Valentina, please. Thank you very much.
Thank you. Thank you very much for inviting me here today. I'm going to present my work, which is a Polytopal discontinuous Galerkin discretization of a coupled non-Newtonian Stokes-Darcy systems. So, I'm first going to give you a brief outline of my presentation. So first I'm going to start with some motivations and possible applications of the Stokes-Darcy system. Then I'm going to briefly introduce the mathematical model and give some assumptions on the viscosity laws. Then I'm going to show you how we prove the well-posedness of the weak problem. Then I'm going to introduce the poly-DG discretization in general and for our problem. Then I'm going to prove again the well-posedness for the discrete problem. Then I'm going to give you some convergence analysis results that are then verified by some numerical simulations. And finally, I will give you some conclusions and possible developments of the work. Okay, so first of all, why non-Newtonian Stokes-Darcy systems are important? They appear in a different branch of science, like in geology, when we think of karst aquifers. So we have underground water that moves in a porous media, in a porous rocks, let's say. So this study is quite important for managing the water resources. Other applications can be found in biology, for example, the plasma filtration through the capillary walls, or more in general, the fluid transportation in biological systems. Transport in biological systems. In industry, we can find the processes of filtration in pharmaceutical or chemical industries. And again, in, let's say, biology or medicine, we have hemodynamics. Often non-Newtonian models are used to model the blood in movement in the capillaries. So these kind of models are important in cardiovascular simulations. So the key challenge of these models is that the fluid exhibit a non-Newtonian behavior. So this means that the viscosity depends non-linearly on the strain rate. And we can have shear thinning or shear thickening fluids. In particular, the shear thinning fluids are the ones in which the viscosity decreases when the shear rate increases, like, for example, blood or some polymer melts used in industry. Shear thickening are, I think, more rare, are the ones that of which the viscosity increases when the shear rate increases. A common example is the mixture of water and cornstarch that sometimes is used in science experiments. You have this mixture. If you jump on it, it's hard. If you step on it slowly, you sink into it. Here we have some viscosity models that are supported by our formulation. In particular, for the numerical simulation, we used the Carreau model, which is this one. But all of these are okay. In particular, we defined these viscosity laws for the Stokes domain and the Darcy domain. The viscosity of the Stokes domain depends on the symmetric gradient of the velocity that we have indicated with d of u. And this big G is one of these laws. For the Darcy viscosity, it depends on the module of the velocity. So here we introduce our first assumption on the viscosity law. So we have to assume that GS and GD are positive and bounded from below and from the top. And moreover, that the function GS of a tensor A times the tensor A and GD of a vector A times the vector A are Lipschitz continuous and strongly monotone. Okay. Here we have the problem and a simple, let's say, sketch of a possible domain. So we have the Stokes regions, the Darcy region that are divided by an interface gamma. In the Stokes region, we have a simple Stokes equation with nonlinear viscosity, and we are considering an incompressible fluid. Moreover, we imposed the Dirichlet boundary, homogeneous Dirichlet boundary condition on gamma S. Gamma S is the boundary of omega S minus the interface gamma. For the Darcy region, we have the Darcy equation written in a mixed formulation. So we have the permeability tensor K and the nonlinear viscosity GD. Again, we have an incompressible fluid, and we are assuming zero flux on gamma D, which again is the boundary of omega D minus the interface gamma. The interfaces conditions gamma are here, but we now see them more in detail. So we have a condition on the continuity of the normal flux. So on the interface, we want that the normal component of the velocity is the same.
Sorry, Valentina. So physically, we are studying the coupled problem between fluid and a porous medium.
Exactly, and the fluid in a porous medium.
The fluid in,
exactly. So
yeah.
Here we have the free flow region that at some point meets a porous medium, and here we have the flow in the porous medium. Okay, so here we have the normal stress balance. So we have the normal Stokes stress on the left that we require to be equal to the Darcy pressure. And finally, we have what is called the Beaver-Joseph-Safman condition, which is a condition on that relates the tangential viscous stress of the Stokes problem with the tangential velocity at the interface. We can neglect the seepage velocity contribution, so the normal velocity contribution, and this is the Safman simplification to the Beaver-Joseph condition. Here we have this ρ0, which is a frictional parameter that we require to be greater than 0. So this was the strong problem. Here we have the weak formulation that is derived in a pretty standard way. So it's here we have that we have a form A that is the sum of a form AS that is related to the Stokes problem, and a form AD that is related to the Darcy problem. We have B that again is the sum of two contributions, one from Stokes and one for Darcy, and we have the sum of the integrals of the first terms. In particular, in the Stokes problem, we have this contribution here that comes from the further interface condition that we had. So if you do all the computation, you can see that you get this integral here on the interface.
The idea would be to discretize the monolithic problem.
Yes.
Altogether.
Yes.
You don't iterate.
Exactly. Here I'm just going to show you which function spaces we chose. So for Stokes, it's the H10 gamma S space with its norm, and for the pressure, we use the L2 function space. For Darcy, we require that the velocity is in L2 with divergence in L2, and we also impose the boundary condition. And for the coupled problem, we define the space X and M, which are the Cartesian product of the corresponding spaces on the two subdomains. For x, we require the continuity of the normal velocity on the interface, while for the space of the pressure, we require that the total mean of the pressure is 0 over the entire domain. And the norms are simply the sum of the norms in the basis of the subdomains. So again, it's all pretty standard. For the well-posedness and stability, we first extended the classical inf-sup, the classical Stokes inf-sup condition to the coupled problem, and we did so by considering inclusion of spaces. So we have that the inf-sup condition for Stokes is, let's say, done using the norm over the space H10, that is the one that we use when treating the Stokes equation. We observe that this space is contained in the space X that we had defined. And so in particular, this means that the norm of the space X is less than or equal than the norm of the space H1. So by using this simple inequality of the norms, we can derive an inf-sup condition that is for the functions, functions V in the space X with the X norm. Then for the existence and uniqueness, we restrict ourselves to the kernel of B. So we define an operator that goes from the kernel of B, that is this X dot, to its dual, and it is defined in this way. So A of U times V is equal to the form A of UV. And so we only need to show the results of existence and uniqueness for A of U equal to F, which is a problem restricted on the kernel of B. To do so, we only need to prove that A is bounded and coercive. And this is very simple because it's only sufficient to show that A is bounded and coercive. I didn't report the computation, but they are very standard. We also proved that A is strongly monotone, but this is actually an additional proof that we did. And then we recovered this stability estimate for the velocity and for the pressure. Both variables are bounded by the forcing terms. Now we can pass on the PolyDG.
Yes. Intuitively, you expected it the other way around. So you have about the inf-sup. I mean, the space H1 is smaller, so having the inf-sup on X, it gives it to H1. So see, just looking at your inf-sup, if I have the norm 1 over the norm in H1 is less equal than 1 over the norm in X. So it seems to me that you have it in the wrong way, the bound.
Here?
Yeah.
Okay. No, I think it's correct.
No. So what is written is correct, but it's not what you need for to have automatically the inf-sup on the border space.
No, because in the classical Stokes, you have this sup of B VP over the norm of V in H1. So from this, you have that 1 over the norm of H1 is less than 1 over the norm of X. So if I substitute here,
So you use the inf-sup for Stokes?
Yes.
To prove this one?
Yes.
Ah, okay.
Exactly.
I see, okay.
About changing the pressure space in the right, like, is it the same? I mean, I didn't follow.
No, the pressure space is the same.
It's the same?
The pressure space,
Is the,
yes, it's always L2. Yes.
Okay.
Okay. Now I'm going to briefly introduce the PolyDG framework. So why it is important, why we chose to use it. First of all, it's geometrical flexibilities. We have polygonal and polyhedral meshes that can also handle complex interfaces and so are particularly useful when we have, for example, need to model the karst aquifer. I was talking before that maybe we have some interface that it's has some strange shape, let's say, and also we can handle heterogeneous media. Then we can also locally adjust the polynomial degree and the mesh size that can be tuned independently per element. So this can be useful in some kind of simulations. We can handle non-conforming mesh, so also agglomerated mesh and mesh with hanging nodes. This is not really related to the PolyDG, but we used the same DG formulation for the Stokes and the Darcy equation, and the interface condition can be embedded numerically via numerical fluxes.
Maybe for some people you need to explain what hanging node means.
Okay, so if you have, let's say, how do I explain it? In a mesh, and let's say on the interface of an element, you have, let's say, this is the interface of one element. Okay, yes, right. Okay, let's say we have an element like this one, and two elements like this. So this is an hanging node. So it's not the vertex of the neighboring element. Okay. Then we enforce the continuity of the function over the elements weakly, and this gives stability, especially when we have heterogeneous and affection-dominated regimes. And finally, we use the equal order spaces for the velocity and for the pressure. Of course, this requires to add a pressure stabilization term. Okay, so we defined a polytopal mesh KH, that is the union of a mesh KHS that was defined on the Stokes subdomain and KHD that was defined on the Darcy subdomain. And we require that each subdomain mesh KHI with I equal to S or D is aligned with the corresponding subdomain. Then we require that our mesh has these two properties, so shape regularity and contact regularity. And finally, we define the face sets, Fi for the interior faces, Fb the boundary faces that are divided in faces for the Dirichlet boundary and faces for the Neumann boundary, and gamma H are the interface faces. Then we define the DG operators. On the internal faces, we have the average operators, which is simply the average of the function over two neighboring elements. Then we have these jumps operator. You can see that one has simply the difference between the values of the function over two neighboring elements. The other has the, let's say, difference, or but in this case, sum of the normal components over the element. On the Dirichlet faces, we have that the average is simply the value of the function on the internal element. And for the trace operators of, for the trial functions, the jumps are the value of the function in the internal element.
You said what contact regularity means, but I missed that. Can you repeat? Contact regularity.
Okay, the contact regularity is that if you have a simplicial submesh, if I recall correctly, and if you have a parameter here, if I remember correctly, okay, let's say you have a parameter rho in 0, 1, and if you have a simplicial mesh such that you have that tau is an element in the simplicial submesh and T an element in your mesh. So you have that tau is contained in T. I believe you have that rho HT is less than or equal than H tau, where H is the diameter of the element. but I can check after
So
the
you say that
presentation.
you have shape regular submesh of triangles and see
Yes.
with size that is comparable
Yes.
to one of.
Yes, then maybe I can check better the definition. Okay, and then I reported this tool that we introduced, that is a trace inverse inequality, that tells us that the L2 norm of over the boundary of the element of a function is less than or equal than the diameter of the element to the power -1/2 times the L2 norm of the function over the entire element. So this is an inverse inequality that we used very much in our demonstrations. Okay, so here we have the discrete problem. As you can see, it's pretty standard. The only thing that...
In fact, it's not an assumption. With your other assumption, you have that. I think.
Yes.
With that assumption, you should have also.
The shape regularities, it's the one with the radius also, I think, of the inner radius of the element.
Don't worry. I think.
Maybe later I'll check better.
Yes, but in the.
But then you just sum up. Okay, it would look to me that you have it given.
Okay. Okay, so here we have this FH, which is the pressure stabilization term that we need since we are using the same polynomial degree for pressure and velocity. And as you can see, I have these penalty parameters here, CS, XD, and gamma, that scale as big O of H, but we will see it in a moment here. Okay, so here we have the penalization parameter C that we used for the pressure stabilization term. As you can see, they scale as the diameter of the element. Here I simply reported the DG formulation of the problem. I'm not going to comment much on it, only that we have these other stabilization terms for the velocity. Again, we have some penalization parameters that scale as 1/h, and that we have this other term here, BH gamma, which is the integral over the element faces of the interface of the Darcy pressure times the jump of the velocity. I comment it because if you notice in BHS and BHD, we have this integral over the faces of the average of the pressure times the jump of the velocity. So this B gamma can also be seen as an average times a jump if we consider a weighted average that has its weight only on PD. Okay, I'm saying this because we will need it to prove the inf-sup condition. So it's going to be important later. Again, we have the discrete spaces and a lot of norms. Okay, for the Stokes norm, we have the classical Stokes DG norm, which is defined in this way. We have the L2 norm of the gradient of the velocity plus this norm that comes from the stabilization terms. And here we have to sum the also the terms that comes from the interface condition that we had. And for the XD norm, we have the L2 norm of the velocity of UD plus the stabilization term. For MH, which is the space of the pressure, we have simply the L2 norm of the pressure plus the contribution from the stabilization term. Okay, as I said, we define this DG norm, which is the classical DG norm for the Stokes problem, and we define this 3 norm DG that is simply the sum of the DG norm for the US variable plus the DG norm for the UD variable plus the stabilization term. Here we have the coupled spaces. Again, they're the Cartesian product between the spaces defined on the subdomains. And here I've defined the 3xh norm, which is simply defined of the sum of the xhs norm plus the xhd norm plus the contribution from the interface. And for the pressure, we have the sum of the 2mh s and d norm and the contribution from the interface. And finally, I defined this 3div norm, which is the 3xh norm plus the L2 norm of the divergence of UHD, and this energy norm, which is simply the norm on xh plus the norm on mh. I know there are a lot, but we actually simplified the notation for this. Okay, so to prove the discrete well-posedness, what we did was first to again extend the general discrete inf-sup condition that we have for the Stokes problem to our coupled problem. Then we had to prove the existence and uniqueness of a problem defined in this way. So AH of UH, PH, VH, QH equal to F, and where AH is defined in this way. So it's like summing up the two equations of our problem. And we need to prove that AH is linearly mapped coercive. Then I'm going to explain what that means. And finally, we recovered the stability estimate. So we have that the norms of the velocity and the pressure are both bounded by the data. Okay, so first, let's talk about the inf-sup. These are three results that we recovered. So let's say two inf-sup conditions, one on using the div norm and one using the xh norm. And then this lemma. So we recovered these two conditions directly from the corollary one, so from this inf-sup condition. So to prove the first inf-sup condition, so the one with the div norm, first we start by a generalized discrete inf-sup for the Stokes problem. Here you can see that we have a term that comes from the pressure stabilization. And this is a result from a paper from Antonietti, Mascotto, Verani, and Zonca. From this proof, from this, this inf-sup condition, we need to prove that this is valid when we use a weighted average over some elements. It was the BH gamma term that I was talking about earlier. And that this also holds for the div norm. So for the weighted average, we define the weighted average in this way. So the average is the usual one on all the faces except on the interface. On the interface, we have that the average is all on PhD. Then we proved this equality, that this equality holds when using a weighted average. And following then the same calculation that are done in this paper, we recover that this inf-sup condition also when using a BH form that contains a weighted average. And finally, to prove that this inf-sup holds also for the coupled problem, we simply consider that by definition, the DG norm is greater or equal than the div norm by definition. And so we recover this inequality starting from this one. Again, to prove that also this one holds, we start from the one with the div norm, and we simply observe that, again, by definition, the div norm is greater than the xh norm, again, by definition. Finally, we recovered also these conditions. And we did so by starting by this inf-sup condition, the one with the xh norm. This inf-sup condition tells us that for all pH, there exists a pH bar such that we don't have the sup anymore, let's say. So we have BH of V bar pH over the norm of VH bar plus pH, this norm of pH time that is greater or equal than the L2 norm of pH. Then we define a variable CH that is equal to the L2 norm of pH times VH bar over the XH norm of VH bar. By definition of XH, we have this condition. But if we take the norm, we have something that is actually equal to the pH, the L2 norm of pH. And then we inserting this term here in this inequality and doing some computation, we can also recover the second, the first condition. Okay, this is just to give you an outline of the proofs. Then for the existence and uniqueness, again, we consider this problem here, and we define this form AH as the little AH of UH VH plus BH VH PH minus BH of UH QH plus SH PH QH. So we are summing up the two equations in our systems. Now we need to prove that AH is linearly mapped to coercive. What does it mean? That this is the definition. If we have X and Y that are two real and reflexive Banach spaces, and we have an operator A that goes from X to the dual of Y, is linearly mapped coercive if there exists a surjection phi in the space of the functional from X to Y, such that we have this condition. And from this paper of Becker and Brack, we recovered this result that if our AH is weakly continuous and linearly mapped coercive, then this problem here has a unique solution, a unique solution actually. I forgot to put the unique. Okay, how we prove that it's linearly mapped coercive? We proved that if assumption 1, that was with the one on the viscosities, and assumption 2, that was the one on the mesh elements, hold, then AH is linearly mapped coercive. We only need to prove that for any UHPH, AH of UHPH, phi of UHPH is greater or equal than this energy norm for UHPH, and with phi as surjection. So first we define phi in this way, and with this definition for phi, it is easy to prove that it's actually a bijection, so it's also a surjection. Then we rewrite AH in this way by the definition of AH and the definition of phi, and then we simply need to use the coercivity of AH, the continuity of BH, and lemma 1.
So alpha and beta are just some numbers that alpha and beta are just some.
Yes, they are parameters that can be properly chosen. In particular, in demonstrating this, we observe that alpha needs to be greater than beta, if I recall correctly. If we choose it in the, they depends on the continuity, so the Lipschitz continuity constant, the coercivity constants, and okay. Then we have this a priori error estimate. Here we have it written assuming different polynomial degrees for all the variables. So we have TS, TD, MS, and MD. But if we are assuming to use the same polynomial degree as we did, we actually have that the energy norm of the error scales as h to the power L, where L is the polynomial degree that we are expecting. So we have, let's say, standard convergence results that we have also for the Stokes and Darcy problems when taken separately.
Is there geometry error here considered? Do you consider geometry error here?
What? Well, besides the mesh assumptions that we did.
I mean, geometric error. I mean, your mesh is just polytopal. I mean, it's just straight, but your gamma is curved. Geometric error
on the geometry. The polygon.
Polygons.
Oh,
yes.
okay.
Yes. We only, besides the mesh assumptions that we did earlier, just this and polygons elements. Okay. Now I'm going to show you some numerical results. First, I'm going to explain some computational choices that we did. We used an incomplete interior penalty formulation. For those who don't know it, this means that we simply have the non-linearity on the left-hand side. If we used, for example, a symmetric interior penalty, we would have had the non-linearity also on the right-hand side. It's not a big problem. It was simply to simplify our computation. Then we, for the scaling, as I've said before, the penalty parameters for the velocity, sigma s and sigma d, scales as 1/h. This is standard for the Stokes problem. It's actually not standard for the Darcy DG formulations. It's usually for Darcy, it's used a penalty that scales as h. For the pressure stabilization, instead, the parameters scale as h, and again, this is standard for Stokes, but not for Darcy. And finally, for the nonlinearity, we used a simple fixed point solver with a tolerance of 10 to the minus 10 to avoid, let's say, errors coming from the nonlinear iterations. So, how we did our numerical experiments, we considered a square domain -1, 1, and an interface right in the middle, so for x equal to 0. Then we considered polynomial degree equal to 2, 3, and 4, and mesh and this sequence of mesh sizes. So we increased basically the number of elements of the mesh. First, we did a first test for a Newtonian case, so for a linear case. So we consider the viscosity to be constant and equal to 1. And then we performed the same test, but with a Carreau model for the viscosity. So the viscosities had this form. Sorry, this should be a MOS. It's a typo. And okay, so here are the results. As you can see on the left, we have the results for the linear problem. As you can see, we have exactly the order of convergence that we expect. 2 for the degree equal to 2, 3 for the degree equal to 3, and almost 4, basically 4 for the degree equal to 4. And we observed the same convergence rate also for the nonlinear case. So this is what we expected. And again, so this test confirmed that we have h to the power L convergence. We used equal order elements with the pressure stabilization, and again, we obtained the optimal order of convergence, and that's it. Then, conclusion, what we did was to propose and analyze a poly-DG formulation for this non-Newtonian Stokes-Darcy coupled system with the Beaver-Joseph-Huffman boundary condition. We also prove the well-posedness and stability for the weak problem and for the discrete problem. For the discrete problem, we used this linear map coercivity that comes from this work of Becker and Black, and we extended it to our setting. Then we prove a priori error estimate that we confirmed numerically. And well, as I said, we got use equal order spaces for velocity and pressure, and we simply had to add a pressure stabilization. So what we could do in the future is to add a Forheimer term to the Darcy equation. This adds analytical challenges, especially in the proof of well-posedness of the discrete problem. Then we could consider try some application with a Carreau-Yasuda model that is sometimes used in hemodynamics applications. So if we want to go more on the applicative side, extend the convergence analysis to account also for the polynomial degree dependence, so doing an HP analysis. and try to relax the shape regularity assumption. For now, we had to skip them because we had to use a discrete Korn inequality in some of our proofs, and it required that shape regularity assumption, but we would like to find a way to relax those assumptions if possible. So this is a possible future work. So thank you for your time and attention. And if you have any questions, I'm happy to answer to them.
Valentina, we already started some part of the discussion, but we have time for other questions, if are. I have a curiosity for what concerns the fact that you used the non-Newtonian fluid for basically for the physical problem and then for the proofs. Was it the key ingredient that was that drove all the difficulties for your proofs for what concern, for example, all the well-posedness and all the technical details? I mean, the problem for Newtonian fluids was already known and already proven, but just my curiosity because it is not my
Yes, of course. Okay. Yes, for the Newtonian case, you have many results, both for Stokes and Darcy problems, and
also for the coupled one.
I think also for the coupled ones. I haven't found much on the non-Newtonian case, especially the coupled case with Politecnico.
Okay.
And yes, it was one of the major difficulties we had in the analysis.
Okay. Thank you.
But with this assumption on the viscosity, the one that I gave
Yes.
at the beginning, it's quite manageable actually. For example, adding a Forheimer term, we already tried some things and we are encountering some difficulties. So it becomes less easy, let's say.
Was maybe a question there?
So have you tried getting a mapping that we usually define from the discrete continuous space to the discrete space to get the discrete in-sup from the continuous in-sup? You know, we usually define that map so that.
Sorry, I didn't understand.
So we usually define a map such that if we are continuous in-sup at the continuous level, so we will be having at the discrete level as well. So that map usually defined between.
Okay, no, I didn't try that. I could try to look into it. What we did was, well, our reasoning was that in the continuous case, we consider inclusion of spaces that gave us that inequality of the norms that we used. And so we tried to have the same inequality also in the discrete space. That was our reasoning. We didn't try with a map. But it
Maybe
could
that
be,
would
it could be interesting.
Yeah, that would directly give you the discrete in-sup.
Yes, I could look into it. Thank you very much.
Are there other questions? This is not the case. I guess we can thank Valentina again. We can continue with discussion and the refreshments. So thank you very much all.